Hello, this is Jason Alvarez with Team 4 of Dr. Shee's Classical Mechanics class, and today our team will be discussing the Mould effect, also known as the chain fountain. So the Mould effect was discovered by Steve Mould, a YouTuber who does science videos, amongst other videos, and at the time of discovery, he was doing a video using Newton's inertia beads, and it was to describe and demonstrate the self-siphoning nature of polyethylene glycol. And instead of using the typical flexible beads and links that are used for this experiment, he used a chain. And when he set up the experiment in the fashion that it's usually done, you take the chain, you wrap it, drop it into a container, you let a little bit hang over the side of the container, and it'll siphon itself out. So when he let it siphon itself out, the beads didn't just uniformly go over the edge and fall to the ground. They created a fountain shape and rose above the lip of the container. And when he reviewed the video, he noticed this and posed the question, why does this happen? Fast forward a couple years later, and you have a pair from Cambridge University, John Biggins and Mark Warner, who did a research experiment on this topic and published their findings in the magazine known as The Proceedings of a Royal Society A. That paper is one that we reference throughout our experiment, and we also use it and its findings as the basis for our hypothesis. So what's our hypothesis? Our hypothesis is that the tension in the chain causes the chain to rise, and this rise in the chain is happening more specifically because the tension is causing the chain to push itself against the bottom of the container, or kick the bottom of the container, if you will. And by Newton's third law, every action has an equal and opposite reaction. Therefore, the table kicks back, causing further tension in the chain. And this final tension, or the sum of tensions, if you prefer, is what causes the chain to rise to a variety of heights over a set time period that we call the Mould effect. Now that we have a hypothesis and our background covered, I'm passing things over to Carlos, and he will demonstrate the experiment.
Hey, I'm Carlos Diaz of Dr. G's Classical Mechanics course, Team 4, and today we'll be describing the Mould effect, also known as the chain fountain effect. All right, let's go.
Hi, I'm Angel from Team 4, and I'm going to explain the math behind what you just saw, along with the analysis of if it worked with our conclusion or not. So, here we go. To explain what just happened, You must look at the chain as it falls as a dynamic, rigid body with an angular acceleration, moment of inertia, a translational velocity, and acceleration. First, look at the tension of the chain, which is equal to its linear density and velocity squared. Then, look at the tension of the chain at the peak of the fountain, coming from the bottle and from the floor. Sum up the forces from both sides. From the container, you have the normal force of the container and a resistive force from the chain. From the ground, there is the normal force from the floor and the gravitational force on the chain at its peak. We can say that the resistance force has a corrective constant, and to find that, we must look at the individual beads of the chain. To do this, we use the relationship between linear acceleration and angular acceleration. Here we use the length from bead to bead as the length to switch between the two. You solve for your resistive force in terms of mass, linear acceleration, moment of inertia, the length of the beads, and then using your system of equations from your tension of chain equations in terms of linear acceleration and angular acceleration, you use that to solve your corrective constant, and then you can use the sum of the forces to solve for the height of the fountain. After gathering our data and producing theoretical results, we created graphs out of the experimental data and produced a trend line that matched our theoretical results and the results found by Biggins and Warner. Although the trend line is skewed, this can be caused by the chain hitting objects like walls or leaves or bushes, or by the chain being picked up by air currents on the fact that we tested ours on the outside while Biggins and Warner tested theirs inside. In summary, the fact that our theoretical and experimental data showed correlation implies that our hypothesis was correct and that the tension for the chain are internal forces caused by the chain being a rigid body.